Hello everyone, my name is James Zhu, and on behalf of my co-authors Joe Payne and Professor Aaron Johnson, I will be presenting our work titled Convergent iLQR for Safe Trajectory Planning and Control of Legged Robots. One primary advantage of legged robots over other modalities such as wheels is their ability to perform highly dynamic maneuvers like leaping and flipping. Recent algorithmic and computational improvements have led to very impressive demonstrations in the past few years. Enabling legged robots to perform these dynamic behaviors is challenging because we need to plan precise trajectories that are resilient to perturbations and errors. But this problem remains difficult because highly underactuated regimes of these dynamic maneuvers cause optimal controllers like LQR to fail. Consider this real-world example of a skier that attempts to stabilize themselves in the air by using the inertia of their arms like a biological reaction wheel. Even though the system would be considered controllable, the high degree of underactuation coupled with the finite time until ground impact makes recovering from perturbations extremely challenging. In this work, we present the Convergent iLQR method, which accomplishes three simultaneous advantages: an improved closed-loop tracking performance compared to standard vanilla iLQR implementation, an improvement in robustness, and simultaneously a decrease in the necessary feedback control effort. Beginning with some preliminaries, legged robots are a type of hybrid system where there's a discontinuous change in state and dynamics at foot touchdown. We can formally define a hybrid system as a collection of domains D, each equipped with a dynamics law F. A point starting in domain I will flow according to the dynamics F sub I until it hits the guard G. At this point, the reset map R is applied, which discontinually updates the state. In this simple case, the reset map is identity for visual clarity. After the reset map is applied, the point is in domain J and flows according to dynamics F sub J. Broadly speaking, the goal of a controller is to bring a trajectory close to some reference trajectory. To analyze the performance of a controller, we can look at variational equations, which characterize the evolution of errors over time. To compute the error evolution across an entire trajectory, we can simply stitch together the continuous variational equations, which are a function of the dynamics derivative matrices A and B and the linear feedback matrix K, with the saltation matrix, Xi, which is the hybrid variational mapping that depends on the dynamics in each mode and the derivatives of the guard and reset maps. This yields a matrix called the fundamental solution matrix Phi that maps the initial error distribution to the final. Next, we define the convergence measure chi, which is the 2 norm of the fundamental solution matrix and represents the largest direction of error growth along a trajectory, or essentially the principal axis of the final ellipse. A value of less than 1 means that all directions shrink in magnitude, whereas greater than 1 means that an error in some direction increases in magnitude. We use this convergence measure to generate safe trajectories for legged robots. In general, the intent of trajectory optimization methods is to plan a system beginning at some initial point to get to some target terminal point, while obeying the system's dynamics. We craft a cost function J, which consists of a cost on the distance from the terminal state, the tracking of the intermediate states, and input effort exerted. There are many methods that have been used to solve this trajectory optimization problem. Here we review the iterative linear quadratic regulator, iLQR, which has advantages of being rather fast and guaranteeing a feasible solution. Additionally, it produces a set of controller feedback gains, which is useful for a closed-loop analysis. iLQR begins with a rollout, where the system is simulated from an initial state using some initialized input guess, handling any hybrid events that occur. Next is the backwards pass, which iterates through the trajectory in reverse, generating a set of feed-forward and feedback gains, which simultaneously finds the algorithm's search direction and the controller feedback gains. After this is the forward pass, which updates the inputs based on the gains from the backward pass and simulates a new improved trajectory. The backward and forward passes are looped until the algorithm converges. iLQR is able to generate an optimal trajectory with feedback gains, but does not explicitly consider if the performance of the tracking controller is satisfactory. We have the convergence measure, which can analyze this trajectory's closed-loop performance, but how can we make closed-loop trajectories more convergent? One answer to this is by adding more feedback effort. If I push harder, then I should be able to get my trajectory closer to the reference more quickly. But in practice, this is not that easy, because high-gain feedback can lead to worsened robustness due to modeling or estimation errors. What we propose here is to design a better trajectory by explicitly taking into account the trajectory's closed-loop performance. In this method, we do this by formulating a new cost function, where in addition to the typical cost on state and input effort, we add in a term that penalizes the closed-loop convergence measure of the trajectory. Skipping over some of the machinery needed to make this work with the iLQR formulation, which can be found in the paper, we tested our algorithm on a planar quadruped with compliance at the knee joints. This system was chosen to model robot designs that have advantage in passive standing, but known challenges in control due to the resonance of the spring dynamics. The first test we ran was taking an initial cloud of errors with a relatively large initial covariance to examine the robustness of the respective trajectories. As we can see, the vanilla controller performs very poorly in preventing divergence of the perturbed trajectories. In comparison, the convergent iLQR does clearly better. We also tested the trajectories under a small initial covariance so that both controllers were able to reliably avoid catastrophic failures. Even in this case, the convergent controller outperformed the vanilla one in terms of both average error growth and applied feedback effort, supporting our claim that we can generate closed-loop trajectories with improved tracking and robustness performance without needing to increase feedback effort. Thank you for listening, and happy to answer any questions.